Recall that last time we were talking about the areas between two curves. So we fixed a function f of x and g of x. We looked at the graph of these two functions. We specified an interval, AB, and then we asked what is the area in the region bounded between these two curves. And it was pretty simple to justify that this was the integral from a to b of f of x minus g of x with respect to the variable x. So the example that we briefly looked at was we had f of x is equal to x, g of x is equal to x squared, and our interval AB was 0, 1. So for such problems, it was convenient to draw a graph first to illustrate. The main reason being that we need to figure out which graph is bounding the other graph. So here we wanted to calculate the area of this region, and we know that the function f of x is larger than x squared on this interval 0, 1. And therefore we could write integral from 0 to 1 of x minus x squared dx. And we remembered that this integral was ultimately equal to 1/6, because we'd get a 1/2 minus a 1/3 eventually. Let's do another relatively simple example. So here let's let f of x equal minus x, x plus 1, x minus 1. So now I have a cubic, and I'm going to set g of x equal to just the negative of this function. So x times x plus 1 times x minus 1. And again, we'll consider the interval 0, 1. It's helpful for us to, again, draw the graph to depict what's going on. Well, basically, I have two bumps, and I can identify that these are two bumps basically by figuring out the roots of this polynomial. The roots will be, because I've factorized things, 0, minus 1, and 1. So I'm going to have this bump from f of x, and then I'm going to have this bump from g of x. And actually, they look the same but reflected. So now we know that f of x clearly is going to be larger than g of x here, and so we can evaluate this area again. So it'll be minus x times x plus 1 times x minus 1 minus g of x, x times x plus 1, x minus 1 dx. So there are a couple things to observe to quickly simplify this. So because this is minus f of x minus g of x will be 2 f of x. So I might as well just factor out a 2. I also notice that this is the difference between two squares, and so I have a nice form for that. So when all is said and done, this is going to be 2 integral from 0 to 1 of minus x cubed plus x, integrated with respect to the variable x. So I get a minus 1/4 x to the 4th plus 1/2 x squared as the antiderivative, and now I just evaluate limit 0 and 1. At the lower limit 0, everything will cancel out. So all I have to do is evaluate at the upper limit 1. So I get minus 1/4, 1 to the 4th power plus 1/2, 1 squared. Well, that'll be 1/2 minus a quarter, which is a quarter. And so when I multiply 1/4 by 2, I'll get 1/2 as the full area. Now, to illustrate that some care needs to be taken when you perform this procedure, you need to, in particular, be careful about these ideas of negative areas that result from our general definition of the integral. So in this case, we're going to have the same f of x and g of x from the last example, only now we want to know the area bounded between the curve and between these two curves in the interval -1 to 1. And so by symmetry, we know that this should be twice, right? So this lobe plus this lobe's area should be twice 1/2 is equal to 1. That's what the area should be. We just know that from geometric concerns. However, what happens if we naively attempt to integrate from 0 to 1 of f of x, sorry, not 0 to 1, but -1 to 1, f of x minus g of x dx? Well, again, we have that simplification that we noted before, -1 to 1 of minus x cubed plus x dx. And so now we're going to have 2, and the antiderivative is still -1/4 x to the 4th plus 1/2 x squared. Evaluate from -1 to 1. I'll have 2. So again, the upper limit is going to be -1/4 plus 1/2 will be 1/4. But then the lower limit is going to be -1/4 -1 to the 4th plus 1/2 -1 squared. When you evaluate this, you get 2, 1/4 minus, well, this will be, again, -1/4 and plus 1/2. So inside I get 1/4. But now I have a net negative, so this is -1/4. And so ultimately I'll get a 0 area, which is, of course, not what the problem was asking. We wanted the area, not the net area of the difference between these functions. And so you need to take a little bit of care because we have this general definition. Another thing that comes up is sometimes we define things in terms of the y variable instead of the x variable. Ultimately, this is just a trick, but sometimes you'll view the graph of two functions and you'll realize that actually I want to integrate with respect to, say, dy instead. So in this example, we have x is equal to f of y is equal to y squared plus 1. So it's a parabola, but it's a parabola that opens out along the x-axis. And x is equal to g of y equals minus y squared plus 2y plus 2. Now, you can calculate the points at which these two graphs meet by simply using the quadratic equation. And I've gone ahead and done that beforehand. And the points will be from y is equal to 1/2 minus square root 3 over 2 to y is equal to 1/2 plus square root 3 over 2. And so now we'd like to get this area. And the first thing is to identify, well, if I'm integrating in the y direction now, then I need to determine what has the larger y value. So it turns out that this g of y that I've defined is actually the function that has the larger y value. And so we have our integral from 1/2 minus square root 3 over 2 to 1/2 plus square root 3 over 2 of g of y minus f of y dy. And so now we plug everything in. And for now, let's suppress these limits. We'll just call them a and b for now, because it's a little bit much to write. So g of y is y squared plus 2y plus 2, and let's just go ahead and add it to all the terms, the negative of the terms from f of y. So we'll get a minus 2y squared overall, and then f of y contributes no y terms, so I have plus 2y, And then I'll subtract off 1 from g of y here. So I have plus 1 dy. And so I know that the antiderivative of this thing is going to be minus 2/3 y cubed plus 2, we'll get a 1/2 we'll get a 1/2 2y squared, so that'll ultimately give me y squared. And then we're going to have a plus y term. And we evaluate this at the limits 1/2 minus square root 3 over 2 and 1/2 plus square root 3 over 2. So this seems problematic, but ultimately, if we're careful, we can consistently cancel out a number of terms that would normally seem like a problem. So I'm going to have minus 2/3 times 1/2 plus square root 3 over 2 cubed plus 1/2 plus square root 3 over 2 squared plus 1/2 plus square root 3 over 2. And at the lower limit, I negate everything, and then I evaluated this guy instead. So I get plus 2/3, right? I just have opposite sign. 1/2 minus square root 3 over 2 cubed plus, minus 1/2 minus square root 3 over 2 squared. And again, minus 1/2 plus square root 3 over 2. And so I immediately see that this should be a minus. This is minus 1/2, and 1/2 will cancel out, and then I'll get a net contribution of square root 3 here. So that will be the leading term. This I can identify as a difference between two squares, and so I can simplify using the difference between two squares formula. This I can identify as a difference between two cubes, and I can again simplify using the difference between two cubes formula. So this is equal to, let's go over here so we have enough room. So this is equal to 2/3, well, the difference between two cubes, I'm going to take this term and then I'm going to subtract off this term as the first part, and so I get 1/2 minus square root 3 over 2 minus 1/2 minus square root 3 over 2. And then I have a squared plus ab plus b squared for the inner term, so I'm going to have 1/2 plus square root 3 over 2 all squared plus 1/2 plus square root 3 over 2 times 1/2 minus square root 3 over 2 plus 1/2 minus square root 3 over 2 squared. So that would be the cubic term, and then I'm going to have plus, I have a difference between two squares here, and the way they line up, I'm going to have 1/2 plus square root 3 over 2 minus 1/2 plus square root 3 over 2, and so I'll get a net square root 3 times a net 1, because that'll be the 1/2 plus 1/2, and then the minus terms will cancel out. And then I have plus square root 3. So this tells me that I'm getting 2 plus square root 3 terms. So let me simplify down over with this cubic term. These will cancel out, and I get a negative net square root 3. These guys have a relatively simple product, and so we'll get 1/4 plus 2 times 1/2 square root 3 over 2 will be the cross term, so I get square root 3 over 2. And then plus, well, the square of this guy is going to be 3/4 plus, this is also a difference between two squares formula, so I reverse the difference between two squares in this case, so I'm going to have 1/2 squared minus square root 3 over 2 squared And so that'll be 1/4 minus 3/4. And then plus, I get a similar thing, but with a different sign pattern here. And I notice I'll be able to cancel out that square root 3 over 2 term. And I have 2 square root 3 from simplifying that part. So now what happens? Well, of course, these guys will cancel out. And so I note that I have 2 and then minus 1/2. And so ultimately that gives me 3/2 from this entire parenthetic term. So 3/2 times 2/3 will give me 1. So I get minus square root 3 plus 2 square root 3. And finally my answer is just square root 3.